Hi guys, Mr. Janowski here. This is part 4 of the chapter 10 slides. In the first part, we learned about the cousins, angular displacement, angular velocity, and angular acceleration. In the second part, we learned a little bit more about tangential velocity and how a wheel rolling down the street, how that actually works. In the third part, we learned about centripetal, P-E-T-A-L, centripetal acceleration. And now we're going to learn about a kind of weird one. This one will be weird. So let's get started. So, no review questions this time. Just think of a time when you've been riding in a car and the car made a sharp left turn. How would you describe what happened to you in plain English? And then how would a physicist describe what happened? So, picture yourself, you're the passenger, and the driver all of a sudden turns the car to the left. I think most people would say in plain English that you were thrown to the right, that there was a force that threw you to the right. Hopefully that makes sense. That jives with, your own lived experience. But how would a physicist actually describe what happened? So I spent a long time making these drawings, so you better appreciate them. So we're going to have Alice driving a big box truck. So here's Alice. This is a very unusual truck. Think of it as like a giant aquarium, basically. The walls and the roof are made of glass so that we can see inside, and the floor is made of ice so that it is frictionless. Physics teachers love ice because we get to pretend it's frictionless. So Billy is sitting on a bench in the back of the truck, and he's ready to go skating. So we're not moving yet, but we're about to. So the truck's going to accelerate for a while. So this is the overhead view. It accelerates for a while. It accelerates for a while. And then it starts doing a constant 25 meters per second, which, if you remember the bloody cheetah, is about 50 miles per hour. It's going just perfectly constant speed, 25 meters per second, and it's going perfectly north. And we're on a perfectly straight, perfectly smooth road. So there's no bumps, there's no swaying, nothing else is going on. We're just going perfectly straight. And the question is it safe for Billy to skate in the back of the truck? So again, this is an unusual kind of contrived situation, but what do you want? It's physics class, just go with it. Is it safe for Billy to skate in the back of the truck? Yes, it is. The truck is moving in a straight line at a constant speed, so its velocity is constant. That means it is not accelerating. If you're in a frame of reference that is not accelerating, we call this an inertial frame of reference. Inertial frame of reference means the rules of inertia hold. The physics we've learned so far work perfectly well. So Newton's laws, this is what I just said. Newton's laws work perfectly well in any inertial frame of reference. So the physics of ice skating will be exactly the same as if the truck were just parked. So as far as Billy is concerned, he and the truck are at rest. He's not going to say that the truck is going 25 meters per second north. He's going to say, no, me and the truck are at rest, and it's the ground that's going 25 meters per second south, which sounds a little bit weird, but that is actually a perfectly valid frame of reference. And hopefully it doesn't sound too weird. You can imagine sitting as the passenger in a car, looking out the window and saying that, oh, the trees are rushing by. Well, the trees don't rush by. Trees never rush anywhere. But from your point of view, in plain English, in your frame of reference, in physics speak, you're at rest, the car's at rest, and the trees are rushing by. So now Billy is going to get off of the bench. I didn't animate this. He's going to get off the bench. He's going to skate to the back of the truck. He's going to turn around, and he's going to do his routine. So he's just, pausing to gather his thoughts. And in his frame of reference, he is at rest. So let me go back to the other slide. So you'll notice here, V truck equals 25 meters per second going up. Up is north. And then watch, here we have V little prime. So we use primes for lots of reasons in science and in math. Sometimes it means derivative. It doesn't mean derivative in this case. It just means, in this case, how do you put it? It's the same thing, but from a different frame of reference, basically. So in the old one, velocity truck, 25 meters per second. Billy, velocity, 25 meters per second. In this one, velocity of truck and velocity of Billy are zero. So in this frame of reference, V primed, those are zero, and it's the ground that's moving. So now Charlie's going to fly overhead in a helicopter, and he's going 25 meters per second north to keep even with the truck. So remember, this truck is a glass ceiling, so that Charlie can look down and see inside of this. So I didn't draw the helicopter, but if the helicopter were here, picture the helicopter look directly overhead, and Charlie's looking straight down on what's going on here. So as far as Charlie is concerned, he is at rest. The helicopter is at rest, and so is Billy, and so is the truck. And it's the ground that's rushing by at 25 meters per second, and the ground is going south in Charlie's frame of reference. Again, sounds a little bit weird, but I don't know. That's what we say. If you're in a car, you say, the trees are rushing by. They're not. If you're in a helicopter, I've never ridden in a helicopter. Maybe some of you have. But if you're in a helicopter that's flying, you're going to, you feel like you're at rest, and you feel like it's the ground that's rushing by. So there's a curve up ahead. So Denise is standing there by the side of the road. The truck is going to turn west, so that's going to be left. So the truck's, from the frame of reference of the ground, the truck is going north, and it's about to turn west. So Denise is standing over here by the side of the road. Don't worry, she's just going to watch this stuff happen. And, the truck is going to make that left turn. The truck's going to make the turn. Charlie's going to keep going north. So the question is, how will Charlie describe what happens next? Remember, Charlie's in a helicopter flying overhead. Charlie is going to say, the ground continues to go south at 25 meters per second. Charlie hasn't changed direction. He's not following the truck anymore. He continues going north. So Charlie's going to say that Charlie and the helicopter, we're still at rest. The ground keeps going south. Billy is still at rest. This is where it starts to get weird. And the truck is accelerating to the west, and it's sliding under Billy. So maybe you can imagine, here, I'm trying to show you. You can't see this. I've got my hand out in front of me flat, my left hand out in front of me. I've got my right index finger pointing down in the palm of my hand. So the palm of my hand is the truck. My index finger pointing down is Billy. So as the truck goes left, the truck slides away under Billy. Seems a little bit weird. So what is Denise going to say in this situation? Remember, Denise is standing by the side of the road. Well, Denise had said, the ground was not moving. The truck was going north, and Billy was going north at 25 meters per second. So after the truck starts to make this turn, Denise is going to say, the ground is still at rest. In her frame of reference, it is. And Billy is just going to keep going 25 meters per second north because of Newton's first law. He was moving in a straight line at a constant speed. The ice underneath him is frictionless, so there's no force being applied to him. So he's going to continue to go in a straight line at a constant speed. He's going to keep going north. And Denise is going to say the truck is going to slide to the west under Billy. So that's a little weird too. And now it gets really weird. What is Billy going to say? So Billy's in the truck. He desperately wants to be in the same frame of reference as the truck. This is very much like you sitting in a car when the car makes a sudden left turn. He's going to say, the ground keeps going by at 25 meters per second, but it's changing directions now. So the ground must be accelerating. So he's going to also say that some force is accelerating him to the right of the truck, and the truck is remaining at rest. So this is all very weird, but this is how you would describe it if you were sitting in a car and the car made a left turn. The key idea here is that Billy is actually wrong in some sense. Billy is trying to do his physics in an accelerating frame of reference. He wants to be in the frame of reference of the truck, but the truck actually is accelerating. So accelerating frame of references are called non-inertial. If you try to do your physics in them, Newton's laws aren't going to work. If you make all of your measurements in a non-inertial frame of reference, and you measure your positions, and you measure your velocities and your accelerations, and you try to figure out what's going on, Newton's laws just don't work. The first law doesn't work. Objects don't stay at rest or in motion in a straight line at a constant speed. F doesn't equal ma if you're making your measurements in a non-inertial frame of reference. So remember, Billy had to come up with this force that was throwing him to the right. This force is what we call a fictitious force. So think back to everyone else's point of view. Charlie in the helicopter looking down, he watched what happens, and he didn't see a force acting on Billy. Neither did Denise. And Galileo, he knew perfectly well how this worked, and Newton knew perfectly well how this worked. There was no force acting on Billy, so Billy for some reason says there's a force, we call it a fictitious force. So think back to your own experience. If you're in a car and the car makes a sharp left turn, you feel some force throwing you to the right. I'm saying this is a fictitious force. You've probably heard the name of this fictitious force. The name of this fictitious force is the centrifugal force, different than centripetal. Centrifugal, Fugal instead of Petal. It is fictitious. It is not actually there. So you can watch any motion at all from any inertial, non-accelerating frame of reference, and you can use Newton's laws, and you can explain everything. So Charlie in his helicopter, Denise standing by the side of the road, they're looking at this, and they can explain everything just using Newton's laws and the physics we've learned so far this year. If you absolutely insist on trying to do your physics using a non-inertial frame of reference and making your measurements in that non-inertial frame, it can be done. We are good enough at math being so unreasonably effective at explaining the natural sciences. We're good enough at math that we can make it work, but you have to make up these fictitious forces to explain what's happening. And then down there at bold, here's the important thing. It's not my job to teach you how to do that. I'm telling you that it can be done, but I'm not going to teach you how to do that. Because in high school physics, you learn the difference between inertial and non-inertial frames of reference. Well, that's what we just did. A frame of reference is inertial if it is not accelerating. A frame of reference is non-inertial if it is accelerating. So we learn inertial frames and how to do physics in them. Once you get to the college, if you go to Westchester, you can take class with Dr. File. And in your third year of being a physics major in college, Dr. File will teach you how to do all of this very complicated stuff in a class called math phys, mathematical physics, just really hard math basically, and how you can do this kind of problem by inventing these fictitious forces, the centrifugal force. But that's Dr. File's job. That's not my job. So one more thing, if you have 27 minutes and 25 seconds to burn, you might actually like this video. So this, way back 1960, these two physics professors at the University of Toronto made this, this neat video. I've watched it a few times, demonstrating different weird things about frames of references. Hopefully the image from this has got you hooked on this. They do some, pretty neat experiments on a little sound stage, basically, with, these neat moving stages, these neat rigs, and they deliver their whole demonstration in this really nice, dry sense of humor. But I think it's pretty funny. So if you're bored, go ahead and watch that. And that's it for this part of the slides. Hopefully that helps.